Welcome to the channel. Our today's subject of discussion is costing test. In this discussion, we shall be talking about step-by-step procedure of costing test cost requirements, calculation of costing factor, interpretation of the results, some examples, and its practical applications. As you know, we have already discussed prerequisites, preparations, and protocols applicable to the standard testing procedure of complete vehicles, that is, motorcycles, scooters, and other power operated vehicles. Now, what is costing test? Costing test is a method of evaluating how far and how smoothly a motorcycle or scooter or a power operated vehicles can travel while rolling in neutral or with the clutch disengaged, typically on a level or slightly inclined road. The purpose of the test is to check for excessive rolling resistance that is due to bearing issues, misalignment, etc. Evaluate drivetrain efficiency, that is for gearbox, chain alignment, and wheel bearings. Assess vehicle dynamics, aerodynamics performance, and friction losses. Support emission and fuel economy research by separating drivetrain and rolling resistance effect from engine-related performance. And finally, investigate any abnormality, such as unwanted brake application, tire deformation, or wheel misalignment. Now, why costing test matters? Therefore, the purpose of the test is to check if a motorcycle goes freely without unnecessarily mechanical resistance on account of dragging brakes, transmission drags, or any bearing issues. If a motorcycle goes too quickly, it may have excessive drag, that is, dragging brakes or tight bearings. And if it goes too slowly, it could mean free play or mechanical faults, reducing normal resistance. Let us come to the test setup and a procedure. The first important consideration is test course requirements. The test course should be flat and smooth for the purpose to avoid interference from bumps, slope variation, or surface friction. The test course should be of sufficient length, that could be from 200 to 500 meters or more, so the vehicle can accelerate, coast and accelerate naturally. The test course should be protected from winds, as winds can significantly alter coasting distance or deceleration time. There should not be any traffic for the purpose of safety and test repeatability. Starting point and end point should be marked to record distance and time. This will be shown in the illustration at a later stage. Now, what types of test courses are the most suitable? The first priority should be dedicated test tracks. They are ideal because they are constructed and used by manufacturers and certification bodies. They are long, flat, or slightly inclined straight section. If dedicated test tracks are not available, second choice could be proving grounds or private roads. If these roads are also not available, third choice could be close public roads, which is somewhat risky. The last choice is chassis dynamometer with coast down mode. These are used for lab-based testing, simulates road resistance and deceleration under controlled conditions. Now, what are now, what should we avoid during coasting test? We should avoid public roads with traffic, roads which are too much inclined or slopy, uneven and damaged roads, windy or inconsistent environmental conditions. Coming to the safety considerations, while conducting the coasting test, the following safety points must be considered. The test should be conducted in a structured environment. There should not be any traffic or obstacle. The rider must wear safety gear all the times. Do not apply brakes until and unless necessary for emergency stops. Regarding test conditions, the surface should be smooth, level or slightly inclined. There should be minimum wind. Tire pressure must be within recommended limits. Chain and mechanical parts must be properly lubricated and adjusted. Brakes should not be dragging. Rider posture should be consistent throughout the coasting test. Now we come to the test procedure. To start with, on the test course, establish measuring points specifically at 50 meters and 100 meters. Then, accelerate the motorcycle to obtain a specified speed of the motorcycle before entering the measured stretch or the measuring points. Shift gear into neutral at the origin point, that is the point O, the start of the measured stretch, and permit the vehicle to coast freely. This shall be shown in the illustration. Adjust the initial speed so that 20 plus minus 2 seconds will be required to run through the 100-meter stretch of the test course. The term 20 plus minus 2 as speed in the context of motorcycle coasting text refers to the target duration it should take for a motorcycle to decelerate naturally, that is, without braking or throttling, from a specified initial speed down to a designated lower speed or to a dead stop within 20 seconds plus or minus 2 seconds. In simple terms, 20 plus minus 2 s means the acceptable coasting time is 18 to 22 seconds. The tolerance plus minus 2 seconds accounts for the minor variation due to mechanical conditions, that is, tire rolling resistance, wind, or surface condition. Therefore, referring to 20 plus minus 2 second means if a coasting test is conducted, say from 60 km per hour speed to 20 km per hour, and the motorcycle takes 19 seconds, it is acceptable. If it takes 21.1 seconds, it is also acceptable. But if it takes 17 seconds or 23 seconds, it is not acceptable. As we have already discussed, we have to measure the time taken to travel through the markers at points 50 meters and 100 meters from the point O, that is origin. In this illustration, this is O point. From this point to this point, it is 50 meters. And from this point to this point, total distance is 100 meters. So if the time taken T1 is for the duration of this 50 meters, then time required to travel through this stretch of 50 meters is the total time T2 minus T1. When we have recorded the distance on time, then we can use the two formulas to calculate the average retardant acceleration in meter per second square due to friction and air drag. And F, that is the coasting factor, which is a dimensional ratio of retarding acceleration B divided by gravitational acceleration. Therefore, B, that is average retarding acceleration, is equal to 100 divided by T2 multiplied by 1 upon T1 minus 1 upon T2 minus T1. And the coasting factor F is equal to B divided by 9.8, where time T1 is the time to travel the first stretch of 50 meters. Time 2 is the total time to travel through the 100 meters, that is full stretch. And T2 minus T1 is the time to travel the second 50 meters. How we have derived this formula? In our subject of physics and engineering, we studied that if we know the initial speed, that is, say it is u, and the constant deceleration, say it is b, then the standard equation of motion S is equal to ut minus half dt square. This is in case of deceleration. But in the case of acceleration, the equation was S is equal to ut plus 1.5 at square. Since deceleration is opposite to acceleration, so instead of plus, minus sign has been used. So we use this equation for coasting test. So for the first 50 meter stretch, if we apply the data of T1, then we get 50, that is the total distance covered in the first stretch of 50 meter, is equal to ut1, that's the time to cover the first 50 meters, minus half bt1 square. Likewise, we apply to 100 meter stretch and we get 100 is equal to ut2 minus 1.5 bt square. From the previous two equations, we get u is equal to 50 plus 1.5 bt1 square, and u is equal to 100 plus 1.5 bt2 square divided by t2. By equating these two equations and by simplifying them, we shall get b is equal to 100 divided by t2 multiplied by 1 upon t1 minus 1 upon t2 minus t1, where b is the average retarding acceleration in meter per second square due to friction and air drag, while t1 is the time to travel the first 50 meters, t2 is the time to travel the first 100 meters, and t2 minus t1 is the time to travel the second 50-meter stretch. After calculating average retarding acceleration, now we can calculate the coasting factors. The coasting factor is equal to F is equal to B divided by G. That is equal to B divided by 9.8. The value of 9.8 is 9.8 meter per second square of gravitational force. This ratio is useful to compare retarding forces relative to gravity, a key performance indicator in force-down tests. Here is an example. Let us assume that T1 is equal to 9.5 seconds, T2 is equal to 20.5 seconds, and T2 minus T1 is equal to 20.5 minus 9.5 is equal to 11.5 seconds. Since B is equal to 100 divided by T2 multiplied by 1 upon T1 minus 1 divided by T2 minus T1, we get B is equal to 100 divided by 20.5 multiplied by 1 upon 9.5 minus 1 upon 11.0. Now, 100 by 20.5 is approximately equal to 4.878. 1 upon 9.5 is equal to 0.1053 and 1 upon 11 is equal to 0.0909. Therefore, B is equal to 4.878 multiplied by 0.1053 minus 0.0909, which is equal to 4.878 multiplied by 0.014. This is approximately equal to 0.0702 meter per second square. From this, the coasting factor is F is equal to B upon 9.8, that is 0.00716, where B is equal to 0.0702, which is the average rate at which the speed decreases due to resistance. F is the coasting factor, which is useful to compare across vehicles. With this, we came to know that the coasting factor, denoted as F, is a dimensionless number that represents how much a vehicle slows down due to resistance like aerodynamics drag, rolling resistance, and mechanical friction. F is expressed as a friction of gravity. The lower value of F means the vehicle has a better coastability. It means that the vehicle is more efficient. Here is another example of the calculation of coasting factor. For example, if a vehicle has a retarding acceleration P of the value of 0.098 meter per second square, then F, the coasting factor, is equal to 0.098 divided by 9.8, that is 0.01. It means the vehicle's deceleration is 1% of the gravitational pull, which is quite minimal, and therefore the vehicle has a good coasting performance. Why it is useful? Because the coasting factor is used in regulatory test, design analysis, and aerodynamics efficiency evaluation. It also helps manufacturers reduce energy losses, and improve fuel economy or battery range in electrical vehicles. Here is a graph comparing typical costing factors for different types of two-wheelers. To start with, light scooter 0.015, city scooter 0.012, standard motorcycle 0.010, sport motorcycles 0.008, electric scooter 0.006, electric motorcycle 0.005, specially designed aerodynamic motorcycle 003. From this graph, we can understand that electric vehicles, that is, scooters and motorcycles, tend to have lower costing factors because of their better bearings, reduced friction, and optimized design. The aerodynamics motorcycle, like racing bikes, have the lowest costing factors, meaning thereby they cost farthest with minimal speed lost. Light scooter and small displacement vehicle usually show higher costing factors due to more drag and mechanical resistance. From the above, we can interpret that in case of short costing distance, the possible cause could be brake drag, misaligned wheels, underinflated tires. And in case of irregular deceleration, the problem could be wheel bearing and suspension issues. If we have long coasting distance, it means good rolling efficiency and minimal resistance. To conclude with, why coasting test is conducted, where it is used. Coasting test is used by R&D departments of motorcycle manufacturers. It is also used by quality control department during production for regulatory emission and fuel economy tests, and finally for troubleshooting in service and repair workshop. The costing test provides the drag data, often referred to as the road test, to also configure the dynamometer accurately for its design purpose. With this, we conclude our today's discussion on the subject of costing test. Please do drop your comments and share your experience. Our next topic of discussion is braking test for motorcycles and scooter. Please don't forget to like, share, and subscribe to receive the similar contents in future too. Thank you and thank you very much.